So this lecture on discrete and continuous random variable. We know what is discrete and what is continuous random variable. In the previous lecture, we see from the distribution function how do you conclude that is one random variable is continuous and or discrete. And we also see that number of jump in this distribution function is at most countable. So it will at most countable jump. If there are no jump, then it is continuous. If there are countably many jumps, it is countably discrete. If it is a finite jump, then it is actually it may be mixed type. If there are countable many disk jump and the other uh, point they are flat, that is piecewise step function, then it is countable. If it is if there is a countably many jump or finitely many jump, but others other than that disjoint discontinuous point, the other in the piecewise interval, if they are not continuous constant, they're not piecewise step function, then it is actually mixed type um, random variable. In our syllabus there is no such mixed type random variable, only discrete. In the discrete there are two type: finite and countable. Infinite is actually countable, and for other than this is only continuous random variable. So we discuss on only discrete and continuous random variable here. Discrete and continuous random variable. So this is a fourth lecture on probability theory. So the definition is the formal definition is this: a random variable and random variable x defined on the that probability measurable probability space defined on the probability space is omega. Omega is a sample space. The script s script s is the event space, is a sigma algebra, and a probability function is said to be of the discrete type. আমরা এটাকে discrete type বলবো, so said to be discrete type or simply just discrete. আমরা just বলবো যে এটা discrete or simply discrete. If I say discrete random variable is actually discrete type random variable if there exists a countable set. It is a countable set subset of real number such that the probability of in this countable set that random variable is just one. The other outside that random variable is zero. So this is called discrete random variable. And the points of E, that means the all real number which belongs to E, which have positive mass. The all point may not be a positive mass. It may be some finitely many value may have positive mass and other may be zero, which have positive mass. In that case, if it is a finite values, it is positive mass, then it's a finite random variable. Finite obviously it is discrete, finite discrete. The positive mass are called jump point. These are called jump point. And this and their probability is called jump of the distribution. That is, the point is called the jump point, and this jump, that jump is their probability, and their probability and the point you see a positive mass is called the jump point, and their probability, what is the probability? That probability it is called the jump of the distribution function. That distribution function df is short form of distribution function. So just looking distribution function, we can say whether it is a countable infinite or finite countable infinite discrete or finite discrete, or it is continuous. Now the total probability must be 1. So now note that some E is a subset of real number such that is a Borel sigma belongs to the Borel sigma algebra. That means a Borel set. If E is a Borel set, now we have this all the singleton set. All the singleton set is actually because it is a singleton set. You know, the every singleton set for x belongs a belongs to real number. Every singleton set is a Borel set. And the Borel set, we just write this as a single just B. Borel set. That means E is a countable union of that. So that's why this is a Borel set. So countable union of Borel set is Borel. So E is a countable set. So E is a Borel set. So then just a singleton set, we know that is a Borel set. The singleton set is a Borel set. We know that in the major theory lecture. Now, then what happened? That means since it's a Borel, the X belongs to that E. This is event. This is an event. They belong to the scriptures. So it is an event. It belongs to the event space. That means the event. So since E is a Borel, X belongs to E is a Borel set. X belongs to E is a event space. So now let X take on the values. Takes on the values on the value xi with the probability pi. So that probability is called pi, with probability pi. Probability pi. So I equal to 1 up to total. So what is this? That means the probability of x equal to xi is pi. But what is probability of xi? X equal to xi, that is actually probability of the set omega such that omega belongs to omega such that x omega equal to, that is the definition of x equal to xi. So that probability is pi for I equal to 1, 2, and that pi must be greater than or equal to 0, and sum over pi is 1. This is a series, so it is a positive term series, so the sum is 1. Oh. Sorry, we write in this last page. Sorry, it is in the last page, so we are going up. So remember that the last page is the first one. Sorry. So what is in? So discrete and continuous random variables, lecture 4. So what we say that the probability of for the discrete random variable x, the probability of that set of all omega belongs to omega, that is we call that is x omega equal to xi, that we call as pi. That value is pi, and pi is greater than or equal to 0. It may be 0 because it may not be countable. It may be finite random variable. In that case, there are only finitely many values that are positive probability, and other rest are 0. So what is E? That E is called a spectrum of x, and what is the E? That is a set of all xi where there is a positive probability. So a set of all xi in real number such that the probability of x equal to xi, that is positive. So positive probability, that is called spectrum of x in discrete case. And that pi summation pi must be 1. This series summation must be 1. Remember, since it is all the pi's are non-negative terms, so you can rearrange the term in the series. So there is nothing called p1, p2 is nothing ordered. So it is not just a sequence of ordered sequence x1 plus x2. if you interchange the term, say x1 plus x2 plus x3 dot dot dot, and you are just interchanging x2 plus x1 plus x4 plus x2 plus x3 plus x5 plus x6 plus x5 plus x8 plus x7, that series sum can maybe different if xi is negative. If some xi are negative, if it is not absolutely converge, it is a conditionally converge, then that sum may be changed. But since it is all the values are positive or non-negative, this, if you rearrange the term pi's, the series will be again same, so that is converge, and you can rearrange the term, so there is nothing, the first term, second term is nothing ordered in here. So the sum is must be 1, that is the condition, and total probability must be 1. So probability of E, that is that x belongs to E. So by the way, this P is actually that P is actually Px. Here P is right as Ps. That P is not the probability space P. This P is actually the distribution P. No, sorry. This is a probability P, right? No. Because this x belongs to E. That is a x belongs to E. This is a element of script. Sorry. So this is that P, that probability space P. So it is a probability on the event, not the distribution. So because the x belongs to E, that is a set in script test. That is a subset of omega. So that P defined on the script test, and that Px is defined on the Borel-Sigma algebra. Now we have this one more definition that is called probability mass function. You know the definition of probability mass function. So what is the definition of probability mass function? So we have some collection of point. The collection of points or number, real number. Points means real number, actually reals. So PIs satisfying that probability of x equal to xi, that is Pi equal to 0 for all I, and the sum over Pi I equal to 1 to infinity, that is 1, is called, that collection point is called is called the probability mass function. That is called probability mass function. Probability mass function, or P, shortly PMF. So it's the probability mass function is a collection of all that PIs, that function actually. So probability mass function of random variable x. So what is probability mass function? This actually is a small f, is actually function from real to 0, 1. Actually that defines only on the positive probability on some countable or finite set. That f of xi is actually equal to probability of x equal to xi. And obviously this is greater than or equal to 0 for all xi in E. And that probability of x, any other value is 0 for if x not belongs to that E, in the not belong E complement is outside the spectrum. And that is a countable set. Remember that is a countable, or maybe it may be finite. So this is called the probability mass function, PMF. And what is the distribution function? Distribution function is just df is distribution function is fx, which is actually, we know the probability of x less than or equal to x, and that can be written in terms of mass function. It is just probability of all, sum over all probability which are actually less than x. At that point where xi's are less than or equal to x, that we add this all probability. So if you know the PIs, if you know the mass function, you can define the distribution function, and from the distribution function you can easily define the mass function. So it is one-to-one correspondence for every distribution function. For discrete random variable there is a mass function, and for every mass function there is a distribution function. So how do you get the mass? That mass is actually easy. It is just f of xi minus f of xi minus. So it's just left hand limit. This is because there is a jump, so it's a right hand continuous. So f of x plus is, remember that f of x plus xi plus is actually f of xi. So since it is right continuous. So if it is right continuous, but it is no, may not be left continuous, so that is that may be positive for, but that positive that number of xi's where it is positive, that is at most countable, that we proved in the previous lecture. Now we define a new function, is a very important definition. It's called indicator random variable. That is a indicator of the set. First we define IA, which is the indicator function. I is the indicator function. It's very important function, indicator function of the set A. What is indicator function of the set A? Say this is any Borel set. So that is x omega. By the way, what is xi ai? What is the indicator function? Indicator function is this. That, IA is a function from real to only 0 or 1. It can take only two values, 0 and 1. So IA of x is equal to 1 if x belongs to that set, and it is 0 if it is not belongs to that set. So it's indicate that output indicate whether the element are in the set or not. So output is 0, that means the input is in the not in the set. Its output is 1, that means that that input is in the set. So using indicator random variable, what we can write that x omega is actually sum over all xi, I equal to 1 to infinity, and that indicator random variable. So that is very, very important. The indicator random variable x equal to xi omega. So this is very important. So x of omega is just this. Why this is so? It is clear, because if omega belongs to that set x equal to xi, the x equal to xi is a set. So what is x equal to xi? That is set of all omega such that x omega equal to, remember, x equal to x omega belongs to that set. What is the meaning of that? That meaning is x omega equal to xi. So if omega belongs to this set or x omega equal to xi, then what happens? Then it is just 1. That is 1, and other value is 0. So if so let omega belongs to some x equal to x10. So omega belongs to x equal to x10, small x10, capital X equal to small x10. Now that omega, if you take a omega such that if x omega equal to x10, then this indicator value gives 1. So it is x10 into 1. Rest, if for other i's it is 0, so it is just xi. So this is just xi. So this in that that's a random variable. The output of the random variable can be written in this form of using express in terms of indicator random variable. So this is important, and we define one more function, indicator random variable, indicator function of the positive part. So we define one more, say epsilon x. We call it as epsilon x. It is called epsilon x, or we may write another notation, say this epsilon x is either 0 or 1. Again, if x is greater than or equal to 0, we define it as 1, and if x less than 0, we define it as 0. So that means it is an indicator of that 0 to infinity closed, or that 0 closed. Now what we can write, that fx is nothing but sum over, this is actually sum over all I equal to 1 to infinity, but we add only that pi, that probability where that xi corresponding small xi is less than or equal to x. That means we write that as x minus xi. So if this x is this xi is bigger than x, then that is negative, so it will be going to 0. And if xi is less than or equal to small x, xi is less than or equal to small x, then in that case this is 1. So it is that we add that pi. So this is very important notation to prove something. Now there is a important example. It's called the simplest example is this. This is called degenerated random variable. X is degenerated at C. C is some real number. It is degenerated at C. What is the meaning of that? It's only one positive probability. So probability of X equal to C is just 1, and probability of X other than that C, that any X, this is 0 for all X not equal to C. So how do you write the distribution function? Distribution function can be written in this form. That is, so this is only one value is pi, only one pi is 1, so it has no sum. So it's just the epsilon of that X minus C. So is only, so what is our then distribution function? The distribution function look like that. So it takes some, say this is my C, this is my C. So before C, this random that distribution function is a red color is a distribution function. This is 0 before C is open, and once it is C, it is 1 just. So this is a mark of 1 in y-axis. This is in y-axis we put fx, and here we put x, and after C this will be just 1. It's only one jump. So this is the simplest discrete random variable. Actually, it's not a random actually. So it's only one value. This is 1. Other than that, this is 0. So it is actually deterministic. So this function is actually this is just 0 or 1. So it is x less than x, it is 0, greater than equal to 6. So what is the mass function then? The mass function is very easy. The mass function is actually f from the probability mass function is from real to again 0, 1. So f of C is just 1, and other than that this is 0. So x not equal to C. So what is the diagram of this mass function? Again, it is easy. The diagram is just at C it is just 1. This mark is 1. This is C, and other rest value are 0. So rest are 0, and this only value is 1 is at C. X equal to C, it is 1. So this is the mass function. Sometime in some book they write they write the mass function, or they draw the mass function like that. But remember, this is not actually the graph of the mass function, because this part, this part, this is not in the graph. The only point is this. That point is the only point. So C comma 1 is the only point in the graph. A positive part. Other point there, every other point is 0. Because it's in a graph that no point of two horizon and vertical point cannot be in the graph, because for same C there cannot be different output. It can be a graph actually. It can be a graph of a function. So some book they write a mass function like that, like that. This is like a mass function in some book, but this is not actually the mass function. Mass function should look like that, some points. But to sometimes that location or to visualize that point may be hard in book. That dot may not be visualized in the book. Some can be missed the dot. That's why they write that they drop this horizontal, that foot of the up to the foot of the perpendicular horizontal line segment. Because remember, this is not the graph actually. This is not the graph. This is the true graph is this, and the rest are there 0. Rest point are 0. The true graph is like that. The rest point are 0. This is not the true graph. This is not a mathematically. It is not a graph of function. So just have to visualize this. So again, next one variable, this is degenerated, and the next one is important random variable. It's called Bernoulli random variable. You know, all of you know that Bernoulli, what is called by Bernoulli P. You know that is there are only two positive probability. This is 0. This is 1 minus P. Sometimes it's called Q. And probability of x equal to 1. This is just P. P must be in between 0 and 1. You know that is called Bernoulli random variable. And and any other values, sometimes we call otherwise it is 0. So we should not write otherwise, we should write like that x not equal to or not belongs to that set 0 1, and it is 0. So what will be the again mass function? The mass function will be probability mass function will be we're not writing that f from r to 0 1. We are just avoiding that writing that. We just write the output f of x equal to the 3 points actually. It is maybe 0, maybe p, maybe 1 minus p. If x equal to actually not equal to in 0 and 1, this is 0. If x equal to 1, this is p, and if equal to 0, then it is 1 minus p. What is the mass function? What is the df, the distribution function? The distribution function clearly is this. It is again 0, 1 minus p, and 1. So up to that less than strictly less than 0 is 0, and then from 0 to 1 it is 1 minus p, and from greater than x greater than equal to 1 it is 1. So what will be the distribution function? The distribution function is easy. That is up to 0 it is 0. At 0 it is just p or q, 1 minus p, it is 1 minus p, and then up to 1 it is that same, and from 1 it is 1. So from 1 and for greater than equal to 1 it is 1. So this is the distribution function of that Bernoulli random variable. So this is the most easiest example of the random variable. Next, we know there are several random variables is like Bernoulli, that binomial random variable, then Poisson, and any other thing. Now what about the continuous? So we are now going to the continuous random variable definition of continuous random variable. So let x be a random variable defined on that omega, that script space, that the event space, and the probability space with some distribution function f, then x is said to be the continuous type, or continuous simply continuous said to be continuous random variable, if that function, the distribution function is continuous. It is not only actually continuous, it is actually absolutely continuous. It's called absolutely continuous. You know, in the real life what is called the absolutely continuous. Absolutely continuous, something different in there. So some function may be continuous but not absolutely continuous, so that should be called absolutely continuous. What is meant by absolutely continuous? A continuous function is absolutely continuous, but there are some continuous function may not be absolutely continuous. So it is obviously it is a continuous, and that means at every point that function probability is 0. So what is this? That is meaning of that is there exists a non-negative function, a non-negative function f, a non-negative function f from real to 0, real to real, and that is actually PDF. That f, small f is called PDF, such that for all x, that capital X can be written as the integration of that minus infinity to x. If we can write, obviously if some for non-negative function, that integration is a continuous function, but any continuous function may not be in this form. So this type of function, once I can write that function of a function like an integration of another non-negative function, then it is called absolutely continuous. So it is absolutely continuous function with this extra property that there is a one more function f. So f is capital F is the distribution function, the small f is the PDF or probability density function for all x belongs to that real number. If such a small f exists, such that capital F can be written in this form, then we call that random variable is absolutely that random variable is called continuous random variable, and that small f is called the PDF or probability density function. or PDF, simply PDF of that random variable x. So this is the PDF and DF for continuous random variable, and for discrete PMF and DF. So this distribution function is both for continuous. Actually, it is true for exists for every random variable. It is just distribution function is capital Fx is just probability of x less than or equal to x. That is always defined because some x less than or equal to x is a Borel measurable function. Is a Borel set. Now for continuous, there is a one concept is called probability density function, and for discrete is the one condition is concept is called probability mass function. So what is the idea? Idea behind this? By the way, what are the different properties of this? We know this since f greater than or equal to 0. For all f, that means the limit extends to plus infinity, that fx is f of that sorry, this is integration of minus infinity to infinity fx dx, which is actually 1. So this is a properties of this density function, that total integration must be 1. And for any two real number, a less than b, may be equal to b, actually a equal to b, the probability of that a less than x less than equal to b, this is actually equal to integration from a to b, that density function, sorry, this x, and this is nothing but p of b minus p of f of b minus f of a. And you know, if B is any Borel set, then Borel set can be written as the union, intersection, and the complement of countable limit of such a thing of this type of intervals, half open, half closed. So we can find the probability of any Borel set using this. If I know the density function, and if I know the density function, we can find the distribution function. If we know the distribution, what is the form? Now the if there is a density function, how do you find the if you know the distribution function, how do you find the density function? That's the important part. So there is a theorem. From small f, you can find the capital F using integration, and it is just a fundamental theorem of integral calculus, that Riemann integral calculus. This is the first fundamental theorem of Riemann integral calculus. You say that if f is absolutely continuous, that means such a small f is exist, absolutely continuous, and f is continuous at x. If that density function is continuous at x, then that small f is nothing but is the derivative of that at that point of continuity. That is called point of continuity. Remember that small f is not a derivative of capital F for all point. It is where that small f is continuous. At that point only, small f may not be continuous function. Like rectangular distribution, the small f has two discontinuity, point of discontinuity. So, but only there are finitely many points, so there will be not any problem. Let us see now. And x is a random variable of continuous type. Here x is a random variable of continuous, or is a continuous random variable. We say simply we say continuous random variable, and that any Borel set in B in the Borel set, Borel sigma, B is a Borel set. That probability of B is nothing but the integration of that fx dx over that B set. So you know how to integrate a function in a set, not in the interval. How do you integrate in a set? That we discuss in the real analysis class in the Riemann integration theory. So this is a very important theorem. we link that mass function density function with the distribution function. What is the idea? The idea is just this. You take this whole real line, we have this whole real line, and there are some probability is spread over all this real line. It's like a total mass is 1. It is spread over the real line. Maybe somewhere it is not spread, it is 0. So maybe it's say think there is a rod, say this is a finite length rod. There's a rod of finite length, and this rod is uniform, say uniform density, or maybe not a uniform density. This is a cross sectional density is uniform. So every cross sectional cross sectional part has a uniform is the same density. This has the same density, but this and this density may be different. Now this rod has the same mass 1, so that means the probability mass. So this mass is 1, say total 1 kg maybe. Now it may not be the uniform rod, so it may be somewhere the smaller density, somewhere the bigger density. So say here is a density is more dense, and is a slightly lighter, is more lighter. So that means is density is the total mass is 1, and every cross sectional area that mass is 0. You know that cross section that mass is 0 because their volume is 0. Because this is area, only area, so area has only that length is 0. So area is maybe some pi r square, but this length is 0, so the volume is 0. That's why the mass is 0. So every point that mass is 0, this is actually a mass density function, but there is a density for each x, and that this does not depend on the cross sectional part. It depends only the x on the x. On the so we can write a that function, a density function maybe look like that. This is very small. Then here it is 0 density, then it is just slightly up, and then is again is dropped down to the 0. So this blue is the that mass density function. Now we consider that this part, that say this is x. So this is actually the density of this height, density at that cross sectional part. But if you consider the whole mass of before x, that mass before x, that function is actually the capital Fx, and this is the small. That blue part is the small. The density is the small, and that mass before that x, and that is always defined. That is the capital X. And we know how to find the density from the mass. So density is nothing but the derivative of the mass, dm dv. But here every cross sectional it is homogeneous. That's why we can write the mass across of unit length. That then we say m is the mass of unit length, the mass in the length. Then we say it is dm dx. And that m is the integration of that cross sectional mass function from minus infinity to x. So the same thing is the same concept like velocity and this displacement. That's capital F is like displacement, a small f is like the velocity. It's just a derivative. And capital F is called the primitive of small f, and small f is called the derivative of f. And we know that small f is the integration of capital F. Sorry, the capital F is the integration of small f from minus infinity to x. And the other way is not true. That Riemann integration theory is called the f dash x is f only for that point where at the point of continuity, at the point of continuity of continuous small f. So where the small f is continuous, in that point f dash x is because otherwise if it's not the point of continuity, the derivative may not exist, actually not exist. If it is not continuous, then f dash x does not exist. So once f dash x does not exist, then how do you write that f dash x is equal to capital F? But capital F exists for every x. Capital F exists for every x, but in some x where f dash may not exist. If it is a discontinuous, that point of discontinuous derivative does not exist. So proof is not, we are not going to the proof, because that proof is just really, you do it in real analysis class. That proof is in Riemann integration theory. So you just avoid this, just omit this proof. Uh, so that means if it is continuous type, then the probability of x equal to x, which is just the integration from x to x, sum f, it is actually 0. So it is true for all x. So for the continuous type. But discrete type, there is no such density concept. And one important theorem is this: whatever the random variable is, whatever it is, x is a random variable, it may be continuous, it may be discrete, then that probability of x equal to a, some point the probability is nothing but the limit t drops to a, that means t always less than a, probability of that t get less than x greater than equal to less than equal to a. So it is lies between t and a. That a, t is always before that, t is always less than a. So this part, we find the probability of this part, and then let t tends to a minus that is an increasing sequence technique, and that is probability of a. In discrete case, it may be positive. For continuous case, it must be 0 because it's continuous. So that limit is actually 0. So what is the proof? Proof is again easy. Just you take a sequence of function, sequence of number t1, t2, dot 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 dot. Everything is less than a. It's actually increased to a. The sequence is increased to a, and we write a set an, which is just tn. The x lies between this set is called the tn an. And obviously an is non-decreasing, and an is actually non-increasing, it is actually decreasing set, and decreased to what? It is actually decreased to the set x equal to a, because intersection of all a n is actually n equal to 1 to infinity. This is actually the set containing only set x equal to a, that set. So it is just that set. So t to a is always there, a is in the all set. For every n, a is tn to a, so a is there, but no other point is there. So it is just decreased to that. And we know that limit, if you just, you can interchange the limit. So limit of the probability an is nothing but the limit probability of, we know in this measure theory class that this limit is it's also true for measure, any measure is also true for probability. We discussed in the first two lecture that this is nothing but that probability of x equal to a. Now this limit is actually that limit, t drop to the a. So this proves complete proof, and this is nothing but f of a minus f of a minus, that the left hand limit, or you can write that as f a minus limit t drops to a. T drops to a means that t less than equal to a, always less than a, and that ft. The same thing, that f of a minus is actually limit of this. This is by definition. So f of a jump, f has a jump, it has a jump discontinuity. You know there are two types of discontinuity. One is called jump discontinuity, where the left hand right hand limits are different, may not they are different, and there's some other discontinuity. This is a removable discontinuity if left hand and right hand limit is equal, but the point value of the point does not exist, or value of the point is different. It's called removable discontinuity, and this is called unremovable or non-removable discontinuity. There are two types of, is oscillating, and there is jump discontinuity. It is a jump discontinuity that if and only if what discontinuity at a, at if and only if that probability of x equal to a, this is positive. This is positive. This is jump discontinuity. So that is, f is continuous at a if and only if probability of x equal to a equal to 0 for all a. So that a, for that a, continuous at a. Now for therefore for it is for random variable is continuous, then it is true for every a. So probability of x equal to a is 0 for all a. So this completes the proof, and we close today's lecture here. Next we discuss on the transformation of random variable. So it's called function of random variable. You know what is called the transformation of different random variable. So before the closing, we just given one example of that continuous thing. So let x be a distribution is a random variable with the distribution function, capital F, where capital F is like that. The fx is 0 if x less than or equal to 0. It is x. It is from 0 to 1. It is x, and it is 1 for x. We can include 1 in the both side because it is continuous thing. So put x equal to 1, then x is 1 and 1 is also 1. So now what is the function look like? The distribution function look like it is up to 0, it is 0, then it is like x, and then it's 1. So this point is 1 and this point is also 1. So this is the distribution function capital F graph of this. And next we if you want to differentiate that, what is fx? It is just f dash x, but it is important that there x cannot be equal to 0 and 1, because at 0 and 1 this is not the this, that small f is not continuous here. So it is 0 and only 1. So because in between 0 and 1 it is 1, and if x is less than 0 or x is greater than 1, then it is 0 because a constant function there, and from 0 to 1 it is x, so its derivative is 1. And at 0 and what about at 0 and x? What about f0 and f? You can't get it from capital F. You can define anything actually. You can define arbitrary. So this function is like the small f function is like that. So this up to 0, before 0 it is 0, after 1 it is 0, and from 0 to 1 it is 1. But the point 0 and 1, you can define anything. You can just closed here, you can add this 2 point here, or you can add above. You can put that as 0, then you include that 2 point. If you put introduce as a 1, if you introduce as a f0 and f1 as 1, then the graph will be like slightly different. The graph will be this thing. Graph will be here it is open, here it is open, and here it is closed. So basically these two function as a different density function, but still it gives the same random variable because it is the same distribution function. Eventually if you take f0 and f1 as like a half, still this is the same distribution function, because if you change only one point, the density function, if you change the density function as only one point, the distribution function is not changed because the integration will not change. If you change your function, if you change your integrand, that function what you are going to integrate, if you change that to the only finitely many point, eventually or in the countably many point, where the countably many point have separated point, or it has a limit number of limit point is finite. If the set may be countable, but the number of limit point is finite, then also this, if you change there that function, that integration does not change. That integrand may be changed, but the integration does not change. You know, it is in Riemann integration theory, if it is separate point, or is the points are may not be, it may be some set as a limit point, one may be finite, but if limit point is countable, that creates some problem. like a dense set. If it's dense set, then it creates some problem. So we're not going into details on that. So we assume there are only finitely many change, and if the finitely many change, the integration does not change, so that distribution function does not change. So that's why that probability does not change, and that's why the random variable will be the same. But your distributed density function may be slightly different at some finitely many point. So same random variable may have different density function. So this is not actually unique, but this distribution function is unique. So for a density function, there is a unique distribution function. For a distribution function, there are maybe infinitely many density function. But we are just take one of them. So because it's actually mainly the same. So this is the graph of small f. So you just given a graph of small f, you can easily draw the graph of capital F, and if you have a capital F, then we draw the small f. Maybe some 1 or 2 point, maybe some finitely many point, you can change that point values. So that's all for today.